Okay. So we're actually going to talk about two different ways to figure out volume. The first way we're going to do is by slicing. So that's going to be this section is volume by slicing. So far when we integrate, we talk about area under the curve. Now we're going to expand our thought here a little bit. If I have any figure whatsoever and I'm coming up with this 3D figure, now I'm not so good at drawing the 3D figures. So, because of that, we're going to use a little book assistance here and have some images. So you're welcome for that. So notice the setup here. Does it look familiar? Well, it should, because this is what we started with when we were finding the area under the curve with all that Riemann sum and the concept of integration. Now we're going to expand that to not just look at the rectangle that's under the curve, but this whole figure. And I've got the width here that I have. Anytime you get smaller and smaller width, that's how we get infinitely many, right, sections. So infinitely many slices in this instance. And that's where we come up with our basic integration. So I'm going to zoom in a little bit here. So we have infinitely many, the limit as the number of slices goes to infinity. Then I'm going to take whatever this slice is, whatever this shape is, and take the area of that in infinitely many areas. That's going to get us our volume. Okay, so this is the general basic rule that we're talking about. So if we have the general slicing method, that's a G. So the general slicing method just means that I'm going to get my volume here is going to equal from A to B of the area dx. Just so my volume, so let's write this. This is the volume of a solid. And that's just in general. So any shape you have, you can just find the area of one of the slices. And then that area infinitely many times, that's going to get you the volume of that. So that makes sense, right? Okay, that is the generic way to find any one out there. We, however, are going to get much more specific. Let's try again. This is the main concept, but we are going to look specifically about revolution around an axis. About revolution around an axis. All right, so we are just going to say, oh, okay, here's a general solid that we can play at, but let's start revolving around an axis. If we revolve around an axis, then we'll see what that actually ends up looking like. Okay, that's how we're going to spend our time. Remember how I just said I'm not so good at the drawing? So here we are. Here's a much nicer drawing so we can figure out what this is talking about. We are going to use the disk method about the x-axis. When I say something is about an axis, that means that I am revolving around that axis. So, I have this function, right, that I'm looking at, and I'm going to take that function and I'm going to spin it around this axis. As I'm taking that function and spinning it around the whole axis, it becomes a solid. And there's our solid. So we are going to be taking this and specifically looking at when you revolve around an axis. That's the type of volume that we are going to be focusing on. All right. And the disk method is the first one that we're going to look at. So let's get specific on this definition, and then we'll see how this plays out. So we're going to let f, my function, of course, be continuous with f of x greater than or equal to 0. So that tells me that this is above the x-axis. So I am starting above the x-axis, right, on the interval from A to B inclusive. If this region R is bounded by the graph of f, which is my function that we were just talking about, the x-axis, because that's making it greater than, right? And the lines x equals A and x equals B, and this is revolved about the x-axis, the volume of the resulting solid is given by this. The volume of the, let me scoot this up, resulting solid is, I'm going to go from A to B here, of pi f of x squared dx. Now, let's talk. Here's the first thing we're going to talk about. Number one, I'm going to get me a color. This tells me that my function is greater than or equal to 0. So all my outputs of this function are going to be greater than or equal to 0. So it's got to be above the x-axis, right? Then I'm going from A to B on this interval. So if my region is bounded by my function, the x-axis, which is that greater than, and the lines, these are vertical lines, right? So those two vertical lines, and this is revolving around the x-axis. My volume here, I'm going to squeeze this in just to see this piece right here. My volume is going to go from A to B. So I've got these two vertical lines from A to B, my function right here and my x-axis. That is what this blue part is. So I'm going to take this region and I'm going to spin that region around the x-axis, and that's the not really, it's kind of like a cone, but not really, just because I knock it off here at B, from A to B, and then I'm spinning that around. So that tells me, what does the end of this look like? Like if I spin that all the way around here, I'm taking the end of this function and I'm spinning it around, what would that look like? A circle. Yes, so that's totally going to be a circle. Now it looks like an oval here just because that's how the drawing is. But if I were to take this little figure right here and turn it and look straight at it, I would have a bunch of circles lined up. Well, our general rule says we're going to have infinitely many of whatever that area is. Well, check me out. That's exactly where this comes from. This is pi r squared, and that is the area of a circle. And just your circle is dependent upon where your function is. So your function is the radius. From the x-axis out to that function is going to be my radius. So as my circles get farther and farther and farther, then my radius gets smaller and smaller, right? That's why I have to look at this radius, whatever the radius is to my function, and that's how I make my circles. Because I'm revolving about that axis, my end is always going to be a circle. So you really don't have a whole brand new formula to learn. You know, your volume is going to be the area of a circle from A to B. Cool, right? Yeah, see, it's not so bad. All right, cool. Let's do some of these.